So in this video, we're going to look at rules for differentiation. We're going to look for differentiation patterns for polynomials. And in the part 2 video for section 9b, we're going to evaluate derivatives at a point, which means we're actually going to be finding the gradient of the tangent at a particular point. We're going to look at the formula m equals tan theta, and we're going to relate it to the gradient of the tangent at that point. And then finally, we're going to look at the relationship between strictly increasing or decreasing functions and derivatives. So finding the derivative of x to the power of n, where n is a positive integer, is something that you will have done in year 11. So it has, in the textbook, it has it written like this. You take the power from the function. To find the derivative, you bring the power down out the front, and then you decrease the power by 1. On the methods formula sheet, they don't use this function notation. They actually use this operator notation. So it's a good idea to get used to seeing the formula written in this particular pattern here. So let's do a couple. There's a couple at the bottom. And the first one has x to the power of 3. So our n is 3. So the pattern says the 3 comes down the front, and our power for x decreases by 1. So 3 minus 1 is 2. For our second one, we've got x to the power of 1. And so the pattern says the 1 comes out the front, and our x power drops by 1, so 1 minus 1 is 0, and x to the power of 0 is 1. So what we've actually got here is 1 times 1, which is equal to 1. I want to touch very quickly on Leibniz notation and making sure that you're actually using the right d something formula in the exam. So if your formula is dy dx and you're differentiating with respect to x, it's dy over dx. And so the pattern occurs on the x value. You bring the power down the front. That's what happens that's what happens with that one. For here, you've got y, and it is a function of t, so your derivative will be dy dt. This formula here has x is equal to 4a, so if you're finding the derivative of it, it'll be dx dA. And this one here has y as a function of x, and so our derivative will be dy dx. Now, I'm going to quickly go through the derivatives for these. So this will become, the 3 stays out the front, the 2 comes down as a new power, and you get 1. So this becomes 6x. This one becomes 2t. This one becomes 4 times the power comes down the front, which is a 1. There's a 1 there. Times a to the power of 1 minus 1 is 0. So it gives us, this is a 1. So this gives us an answer of just 4. This last one, pi, is just a normal number, so we leave it at the front. The power comes out the front, so it's 3, and then x to the power of 3 minus 1 is 2. So this derivative is 3 pi x squared. I want to have a look at working with derivatives when you've got a number out the front of the x. And to do that, it's best if we have a look at derivatives and gradients in the form of their graph. So first of all, let's have a look at what happens if you've got a function that's equal to a constant. So I've got one over here, f of x is equal to 3, and what you get is a horizontal line. And a horizontal line has a gradient of 0. So the rate of change of this line is 0. So our derivative is 0. So if you're finding the derivative of a constant, it's 0. This value out the front that we talked about before, you can think about that as a vertical dilation, or if you like, a reflection of a graph. And so you can see over here I've got x squared and then I've got kx squared. So I've assumed that k is a value greater than 1, so it gives me something a little bit steeper. And if I'm looking for the derivative of those graphs, what I'm looking for is the gradient of the tangent. And you can see that's the tangent for the point on the original graph, and the tangent on the dilated graph is much, much steeper. And in fact, it is whatever it is increased in steepness by a factor of k. So let's have a go at doing some derivatives right down here, down the bottom. We've got the derivative of 2. 2 is a constant, and so the derivative of a constant is just 0. We've got a derivative of 10x squared. So the 10 stays out the front as a multiplier. And then we just do our derivative using our power up here, that we've got our power of 2. And that becomes, the 2 comes down out the front. The power drops to 1. So we've got 10 times 2x to the power of 1, which is just 20x. Continuing along with this idea of looking at graphs of the functions that we're trying to differentiate, we use derivatives of polynomial functions where we'll just differentiate each term by itself. And I want to take just a minute to explain why we can do this. So you can think of this function h of x as made up of two functions, f of x as x squared and g of x as 2x. And here I've drawn both of those functions. I'm going to look at this specific x value here. At this specific x value here, the gradient for the parabola is -2. And at this point here, the gradient for that straight line is 2. In fact, the gradient of that straight line is 2 all the way along the straight line, which is why it's straight. And at this point here in the center, the gradient of the parabola is 0. And again, the gradient of the straight line is 2. When we have a look at the function that is the sum of those two functions, h of x, I've drawn it over here. So I've just copied this picture, put it over here, and put the sum function in. And this is it here. And you'll notice that along this white line here, where the gradient of the green graph was 2 and the gradient of the yellow graph was -2, -2 plus 2, when you add them together, gives you a 0. And at that point, at that x value, we actually get a 0 on our sum function. At this point here, we had that the gradient of the yellow line was 0, the gradient of the green line was 2. 0 plus 2 means that at that point, our blue graph has a gradient of 2. And so you can see that adding the functions, you can just add their derivatives to get the derivative of the sum of those functions. So for this one down the bottom, what that means is that we just find the derivative of each of these functions as we go. So the derivative of x squared is 2x, and the derivative of 2x is 2.